just want to thank Julius for giving me the opportunity to do this talk at CCRMA, and you know, it's a very special day for me, and I know that John will come in too, and Charling, so I'm very proud of that. And thank you, CCRMA, thank you, Julius, and thank you for having us this week with my colleagues Romain and Maxime. So I'm Tanguy Risset, and I will be talking about this compilation flow from audio DSP, namely Faust program, on FPGA. And this is a work that I've been doing in my Emeraude team that I hold in Lyon, where Romain is working now. And I will give a brief presentation of the team. Then I will take this opportunity to go a little bit more in detail in the description of FPGA, because I think it's a technology that has been existing for years and which is not that complicated to understand. I mean, it's very different from computers, so everybody can understand how FPGA is built. And then I'll go on the core of the talk, which is focused on the Faust 2 FPGA compiler, which is a new compiler that allows us to program an FPGA from a Faust source program. Okay, so just a word about my research team. So this is a zoom of the origin of the member of the team. We are currently 5 permanent people in Lyon. And well, many of you know Romain because he did his PhD here, Romain Michon, and maybe some of you know Yann and Stéphane, who were working in Gram in Lyon for many years. And I've been working with Florent in another area. I come from computer science and compilation, and we were working on software-defined radio, okay? And we decided 2 years ago to create a team together with Yann, Stéphane, and Romain, basically a collaboration between Gram and our institute, which is INSA and INRIA. And that gave birth to Emeraude. Emeraude stands for Embedded Programmable Audio Systems. So we are targeting audio system, but we have a background of compilation on embedded systems. So we want to map this audio system on embedded systems. These are the domain of expertise that probably you have also at CCRMA. The one thing which is particular is that we have one guy which is a very well-known guy in arithmetic for FPGA. That's Florent de Dinechin. I will not talk about that today, but he's a world specialist of arithmetic for FPGA, and this is useful for DSP because arithmetic is very important for DSP, of course. Okay, so that's a global scheme of the team. Just for you to know that I will only talk about this axis, DSP compilation on FPGA. Well, we have other research axes, and of course, if you are interested, don't hesitate to ask me about this other direction. So, okay, so let's now move to FPGA and HLS. HLS stands for High Level Synthesis, and HLS is a very important technology that enables us, I mean, us like, you know, programmers, to program FPGA, which were programmed usually by hardware engineers. So we all know about the Turing machine, which is the model for the computer, okay? And Turing and von Neumann built this computer thanks to the access to random access memory, which makes the Turing machine more tractable. So in some sense, the Turing machine is a model for the actual computer, the von Neumann computers that have been using for years on your workstations. But in the meantime, in the old days, there was other computation model, and especially there was one which was the cellular automata model. So you have a bunch of very simple automata which are connected one to another. It might be a 1D automata on a line, or a 2D grid. And well, you might have heard of Conway's Game of Life. So this kind of application, it has been very much studied in the 60s. And in fact, this model is the equivalent of the Turing machine for FPGA. It's a model of computation that has been used for building FPGA. So FPGA is a set of very simple automata connected together so as to build a computing system. So Yeah. Sorry. So what is an FPGA? An FPGA is a grid of configurable cells. So these are the cells, and these are the real cells on the FPGA. So the difference is that you will have more routing wires, so you will not be limited to the connection to one neighbors, but you can connect to other neighbors. So what is in this cell? This cell contains a very simple function of 4 input, 4 logic input, I mean 1 bit input, and 1 input. So we are talking about, whole logic. So you can implement any function of 4 input and 1 output, any logic function. And as we have only 4 input, so we have 16 possibilities. So we can use a lookup table to compute the function. It's not a real computation with gates, it's a lookup table. So this is why these cells are sometimes called logic cells, sometimes lookup table or LUT. Okay, so with that, and with this connection network, you can build any logic function, okay? And to have a computer, you need sequential circuits. And to have sequential circuit, you had just a register, a 1-bit register in each cell. And with that, you can do any sequential circuit. If you need a 32-bit register, you take 32 cells and you have a 32-bit register, okay? So the idea is that you have a huge number of cells on an FPGA. So that's the way it is, and the programming of an FPGA is just the configuration of this grid. Each box here is configured with a logic function of 4 input and 1 output, and possibly using the register or not. And the network here is configured to route the signal between the wire. Is that clear? Okay, so this is an example of a configured FPGA where in red you can see the circuits which has been implemented on the FPGA. So we have configured this block to have this function, this block to have this function, and we have connected the wire together. So these wires have they have transistor on it to route the signal from one logic cell to another. So this is why we call it reconfigurable computing, because it's a circuit, okay, it's really technological, it's exactly equivalent to a circuit, but it's reconfigurable. If you build a circuit with VLSI, it's not reconfigurable. Here, you can map this circuit, and then after you can reconfigure it into another circuit. Okay, so when we are to program an FPGA, what we need to have is a circuit. Yeah?
Is reconfiguration possible at runtime? Like, can you have the FPGA like change its own circuits?
Yeah, you have some of this feature on some FPGA. You have been that for a long time, but it's not very efficient. In some sense, it's very complicated because you have to separate a certain zone that you reconfigure while the rest is running, and it's not really the way that it's used in industry, at least. There is a lot of research on it, but it's not really efficient today. So, okay, so when you, the difficulty of programming that is to build a circuit. Okay, building a circuit, designing a circuit is complicated, but once you have the circuit, you can program the FPGA, and program the FPGA means sending all the configuration to all the small boxes and all the configuration to the routing wires. So it's a lot of configuration bits. It's called a bit stream, an executable for FPGA. And then once you have configured the FPGA, it just runs, and there is a clock which is gating all the register, and then the circuit is running. So that's quite simple. So that's why we don't really program an FPGA, we configure an FPGA. So this slide, so it's quite old now, but it's just to show you that actually the effort in FPGA designer is not spent into the logic, but rather into the routing. And so it makes sense that, for instance, having an FPGA that, as we discussed yesterday, may be very useful for routing for having a lot of channel on a system, for instance, because there is a lot of space on the FPGA chips which is taken by the the network between the cells. So the blue here are the logic cell, and the rest is the routing. And this is a very old FPGA, and it grows not exponentially, but the routing is growing more rapidly than the number of cells. Okay, so here are some comparisons. Okay, an FPGA is like a circuit, but it's less efficient. So for instance, for emulating one gate on an FPGA, you need a certain number of gates one gate on VLSI, you need a certain number of gates on FPGA. So if you have a 1 millimeter ASIC, you will need approximately 50 square millimeters for an FPGA for emulating this ASIC. And the FPGA will run slower because as there are transistors on the wire, the signal is slower than in your digital circuit where the path will be direct. But the great advantages is that the cost of the FPGA would be much less than the cost of an ASIC. Okay, so that's why FPGA are used for prototyping a lot. Like if you want to build a circuit, you first prototype it on FPGA and then you implement it on the circuit. Okay, so that's the most important thing for FPGA. This was very original at that time, but during this year, because these have been existing for more than 30 years now, there are other components which are important on the FPGA chips. So for instance, there are many small multipliers that we call DSP blocks, around 24 bits multiplier. So these are fixed points. On the most recent FPGA from Xilinx, they introduced floating point multipliers. And they are very useful, especially in DSP. There are also many small memory blocks, around 10 kilobits, which are spread over the FPGA. And which is more important, there is a computing system. There is a complete system on chip, including an ARM CPU. So this is a picture of the zinc FPGA that we use. So the orange part here is the FPGA, and this is the CPU. So you see that the CPU is communicating directly with the FPGA, and it's also communicating with the memory outside of the chip. So this is very useful because usually when you have to have a hardware acceleration, not all of your program has to be accelerated. So you can put your program on the ARM and then put the part that you want to accelerate on the FPGA. Okay, so this is the FPGAs that we are using. So this is, for instance, a demo, the board that we use for our demonstration. So this is a Zibo board, which contains a Zinc 7010. It has 2 ARM cores that might run up to 1 GHz. It has 20,000 logic cell or LUT. It has 80 DSP block and 60 block RAM of 36 kilobit each. And the FPGA itself is running, it's not running at 1 GHz, it's running around 200 megahertz, 200 to 400, it depends on the design. Okay, so that's for the hardware. Now, how do you program it? So the traditional way, and it has been like that for many years, you design a circuit. And designing a circuit, well, you don't have to design it at the gate level. You can use integers, you can use adders, and you use the so-called RTL level, register transfer level. And then you go through synthesis tools. And then this is a process which is very long because it's a mapping the different logic function to the blocks and routing the connection to the wires. This is NP complete, so there are heuristics, and this synthesis is taking very long, much longer than a classical compilation. But still, it's difficult. I mean, if you are to write, even at register transfer level, it's difficult to write a circuit, and it takes a long time. So you use this language, VHDL, and so on. So what is the real revolution is that approximately 10 years ago, there was the industrial appearance of HLS, so high-level synthesis. So HLS proposed to write a C++ program and to map it to a circuit. So one of the difficulties of writing this circuit is that you have to express the parallelism, okay? So we don't really, it's difficult for us to think in terms of parallelism. And the HLS tool will take some specification written in C or C++, which is sequential, and parallelize it to a circuit. And then you have to use the synthesis tool again. But yet it's much easier to write the program to express it in terms of high-level language. So that's called high-level synthesis. Even if for us, I mean, for computer scientists, C or C++ is not really high level, but it's better than register transfer level. And so just a few words about HLS. What does it mean, HLS? HLS is just a word for actually parallelization, in fact. So what HLS is good at is finding parallel instruction, like these two parallel instructions. You see that there are no dependency between the instructions, so they can be executed in parallel. But of course, the semantic of the C, it's to be executed in sequence. And the other thing which is very important is loop pipelining. I don't know if you have heard of loop pipelining. It's a very important way of optimizing programs on machines that have many cores, for instance. So if you have a loop like that, with three instructions that I call read, compute, write. If you execute, the semantic of this loop is this one. You read, compute, write, and then you execute the second iteration. Now, so this is a pragma which is given to the HLS tool, which we use, which is called VITIS HLS. And VITIS HLS is able to compute this loop this way to overlap the second iteration with the first one, and the third iteration with the first and the second. Okay, so it means that basically this will be done automatically, provided you give the pragma to VITIS HLS, and it will parallelize your program. And this is very important because I've been working a lot on parallelization. Automatic parallelization is a very difficult problem in general, and the tools, the HLS tools, have managed to render it efficient for some program at least. So what we are trying to do, and the real challenge of the project that we have been talking these days, is that we are trying to do real high-level synthesis. It means that we are trying to synthesize a circuit from a very high-level description language, which is Faust. So the idea is to use the Faust compiler as a front end to the HLS tool, which is not very common because the HLS people are used to have programs written by hand in C++ by people. And it's also a challenge because the Faust compiler is supposed in general to go to a sequential compilation like C++ or language. So, so this is what is very original in our project, and this is what I will explain now. Okay, so this was for FPGA and the methodology of programming FPGA. Now, what we've been working on with Maxime and Romain is this Faust to FPGA compiler. So I assume that Faust is known by everybody. Is there anybody who doesn't know Faust? Faust language? Okay, so I'm going to skip this slide. And if you don't know Faust, please go on the Faust website. You will see that it's very interesting. So this is a representation of my FPGA. You have the logic cell here. You have the processing system here. And as we are doing audio, we are connecting the audio chip directly on the FPGA. So what does it mean to compile a Faust program? So if I have a Faust program, in this program, I have some of the computation which are I cannot see. Some of the computations are at sample rate, and some of the computation are at control rate. Okay, so this is a slider which controls my transformation, and the slider has no real-time constraints. So what we want to do is that we want to map what is real-time, what needs real-time on the Faust IP. For IP stands for intellectual property. It's a name that is used in this domain for a circuit. So the Faust circuit, the circuit that will implement this Faust program is here. But what is really on the circuit is the the computations that are done at sample rate. What is done at control rate, which is basically the handling of the slider and it's giving its information to the program, is done on the ARM. And this is what we call the controller. So basically, our compilation flow will generate two programs, one for the Faust IP, one for the control program. And fortunately, this is something that is very well done by the Faust compiler. Okay, the Faust compiler already separates what is at sample rate and what is at control rate. So now, this is a logical view of our compiler. We start from a Faust program. We call twice the Faust compiler to generate two C++ programs. One is hardware.cpp, the other is software.cpp. Hardware.cpp goes through high-level synthesis and synthesis, logic synthesis, and so on, and gives the IP, and software.cpp goes through GCC to an ARM executable that will control the hardware on the IP. Okay, so the system that we have implemented, and there is a photo here of the first prototype. Here is the IP on the FPGA. So you have the ARM here, you have the executable controlling the IP. They are connected with a protocol which is called IXE, which is given by Xilinx. So I forgot, maybe I mentioned this is Xilinx material, so we are all working with Xilinx. And the IP will be interfaced with the codec through an I2S circuit that we have designed especially for that. And then we can control the IP either by the hardware interface, like this one, for instance. This daughter board was built by Maxime for controlling what is running on the FPGA below, or on a software interface. I will show you. You can have a GUI on the machine. So the last thing is that we have also an access to a memory, a big memory, because we have some memory on the FPGA, but not enough to compute all well, to use, for instance, echoes. So we have to have access to the DDR memory, and this is important because it's not very common in FPGA design, and it was very difficult for us to achieve that, but we made it. So we have a prototype running on this resulting audio system. The first version starts from 2020. So I guess you understood, we are compiling the Faust program to CPP. Then we are using VTSHLS, which gives us a VHDL program. Then with the I2S VHDL, we are using Vivado to map the bitstream on the FPGA. So the first version was just one single compilation flow. And the version that we have now performs this hardware-software partitioning that I talked about, which is very important because the program was too complex to be mapped on the FPGA if you don't separate the software. It performs DDR access. There is a number of parameters that you can change. You can change the audio codec. You can change the sample rate, the sample bit width. You can change the number of audio channels. You can change the target board. So it's a real compiler. You see, it's very important because before that, when you are to design a circuit on FPGA, you basically do something for one particular configuration, and if you have to change the configuration, you have to redo the work. Now the compiler is something which is very parameterizable. Okay, so we have hardware or software interface. I will show you that. And the original motivation for this work was to have a very low latency from analog to analog, okay? And we were able to reach this 11 microsecond latency, and I will talk a little bit about that. So the compilation time here is about 15 minutes, okay? You have to have in mind that it's not like compiling a C++ program, it's a little bit more, but that's standard in FPGAs. So this is the interface of our program running on the FPGA, either the hardware interface or the software interface, and this is inherited from the Faust environment. Okay, so we can reuse this component because it's running on the host computer and goes through the UART to the FPGA. Okay, let's take a simple example. So simple, I don't know if it's simple, but So this is a program, this is a sine wave implemented with a big quad filter. So I guess that's Julius who wrote this program. And we use it a lot for showing our compiler. So in this sine wave, you have a computation here, which is done at sample rate. So if you don't understand that, then you can ask Julius. and then this computation uses this parameter S, C, TH, which are computed here, and which themselves depend on F, which is here, and F is actually frec, which is a slider, okay? So we can see that all this computation can be executed at control rate. And so we hope that they will be mapped on the FPGA, of course, on the ARM, sorry. Because if we are to be implemented a sine wave using a sine, so that would be, you know, be useless. So fortunately, this will be implemented on the ARM, and the rest will be implemented on the FPGA. Okay, so this sine.dsp goes into the Faust compiler that we call twice. Once for generating the hardware.cpp and the software.cpp, sine app. So if you are familiar with the Faust compilation process, the Faust uses an architecture file, which is here for the hardware and here for the software. And this architecture file is supposed to interface with the resulting, the target hardware. So in that particular case, this FPGA.cpp is the IP. It's a circuit with its standard interface. So it's very important because this program here do not change, and we have the same interface for many Faust programs. So it means that we don't have to rebuild everything for every new program. Then this is compiled with the Xilinx tool suite to the Vivado, to the Faust IP, and this is compiled to the executable. So that's the same program that the same scheme that I showed before, okay? So let me show you very briefly some part of the control and the IP. So this is the compute, this is in the IP, so that's what is implemented on the FPGA, and that's what's implemented on the ARM. So actually the C++ program are much longer, but what is important is here. And what you can notice here is that you have these three controllers which corresponds to the sine, cosine, and the computation of the slider. And this is computed on the ARM. And then this F-controlled function will be an input to the circuit, you see. So there is a connection between the software and the hardware to connect, to give the control, and the controller are used here on the circuit. But the sine wave is computed on the ARM, and the big quad filter is computed on the FPGA. Okay, so the last code is the interface of the IP. So it means what I'm showing here is this circuit here. So you can see you have two. So you have the audio channels, which will go to the I2S protocol. Then we have the controller, which goes to the ARM. And then we have the RAM, so it's a little bit specific. The RAM, you have to have a specific protocol. So these pragma are given to VTIS, to Vivado, so that they will implement, to VTIS HLS, so that these three parameters will go to the AXLite. So it means that they will use the same bus to go to the ARM processor. And this one, the RAM, will use another bus to go to the memory. So this is, okay, this is something that we did not invent ourselves, okay? This is the way you have to do it if you want to use VTIS HLS, but it's very convenient and it works. I mean, and the body of the IP is very simple. If it's the first iteration, we initialize the constant, and else we compute we execute the function compute my DSP, which I've just shown you, okay? Okay, so so that's it for the flow. So how did we obtain this very low latency? So what we have is that we have the Faust computation for one sample, which introduce a one sample delay. Okay, the computation of the sample is just one sample long. So we have another one sample delay which is introduced by the I2S interface, and now we realize that if we want to go from analog to analog, we have many samples in the codec. Okay, many sample delay depending on the configuration of the codec. So what we did, and that's Maxim's work, we bought a much more efficient codec, ADAU 1777 and 1787. And by running these codecs at different sample rates, we get better and better latency from analog to analog until we reach this 11 microsecond latency for, of course, it's a very high sampling rate, but we reach that latency, while what we have seen in the literature, people could not go beyond 180 microseconds. So that's a very good result for us, even if we have not yet applied it to a particular application, but we're working on active control for the in the project currently. Okay, so here are some performance results. So just to show you that in some sense we have a real compiler, we are able to compile many programs with many different parameters. And this shows basically that the complexity in terms of size, okay, in terms of lookup table, is more or less linear for this kind of process. So we have the Bell program here, we have the echo, which is n parallel echoes. And this is the maximum number of lookup table on the ZIBO, on this one. But the ZIBO is a very small FPGA, okay? The Z20 has 3 times more lookup table. The Genesis board has even 5 times more lookup table than the Z20. So there is, we believe that we will not really have a problem for resource constraint unless we target very complicated signal processing. But if we look at latency, so the latency I'm talking here is not the analog to analog latency, it's the latency of computing one sample on the IP, okay? And computing one sample on the IP is expressed in terms of number of cycles of the FPGA. And because the echo program is using the RAM, each access to the RAM is about 50 cycles on the FPGA. And then if you have too many accesses, then you will have, it will take too long. And this is the time, like 22 microseconds. This is the time of one sample at 48 kilohertz. So if we are at 48 kilohertz with a FPGA running at that speed, we will only be able to run like 18 echoes in parallel. Okay, so that's a limitation. And we're working on how to overcome this limitation, which is probably the most important bottleneck from the performance point of view. Okay, so let me just, if I have 5 minutes, yeah, just let me show you how it works. So what I've done here is that I've compiled the, so I'm gonna go here. And I have already compiled my program on my machine because the compilation takes about 15 minutes, so I don't want you to wait for that. And I'm just gonna map it on the FPGA by typing Cifala Flash. Yeah, thank you. So probably, I don't know if people see. So the light is on here, and if I switch on the okay, so this program is a virtual analog, and then I can have the GUI which controls, so if you can see it, so I can have a software control, okay, and I can also switch dynamically to the hardware control. Just there is a switch here. And now I control it with the hardware. So, okay, so this is just to show you that the use of the compiler is quite easy. And And then if you are interested by this tool, it's available on GitHub, so you are encouraged to download it. So the only thing is that you have to download Xilinx tool to use it. And Xilinx tools are about 100 gigabytes on your computer. So that's something that you have to know if you want to use the Cifala toolchain. Okay, so that's a summary of our first prototype, I mean, really working prototype of Cifala. So we have trying to optimize latency. So we have this one sample strategy. So we compute one sample by one sample in order to have the minimum latency. So it means that there is no overlap between the computation of the different samples, and we could improve performance by overlapping that, but we will decrease latency. So we will probably work on that. So I mentioned all the tunable parameter, and we are working on these points. So as I said, optimization of the memory accesses. Something I've not mentioned, but all the computation are done in floating point, which is not very efficient for FPGA actually, because usually FPGA use fixed points. It's much more smaller in size. And we have a specialist that can help us in translating Faust program in fixed point computation. We have no loop in the C++ generated by Faust. Maybe you know that. Faust is unrolling all the loop. So that's nice for some application, but for us, it's not very what we want because we cannot control the level of parallelism. Okay, everything is the most parallel. And sometimes it's not what we want. And of course, and that's what I mentioned before, we have no pipeline between the samples. Okay, I'm almost finished. So this is just a recap. This is a picture of the Minimoog. Minimoog was written by Romain Michon, I guess, a few years ago.
No, Julius.
Oh, that was Julius?
Yeah, I did it for Pat and
Steve
Dallas working for ADI. It was actually sponsored by ADI. ADI got, Analog Devices got interested in incorporating Faust into their development workflow and their libraries, and so they commissioned Pat to do this, and I did the software in Faust.
Okay, yeah, sorry about that. I'm misleading with another.
So it's a gift from ADI. Is what
okay,
it is.
so maybe I can show you because we were quite happy. I mean, we just tried it and it worked. So
it's pretty much the whole thing.
Yeah. So what I say is just I import because I've already compiled it again. So it's low volume because well, we don't want to crash our ears, so by default we compile it with a low volume. And if
0.1 is my standard.
Okay, so I'm gonna flash the.
As I recall, that whole thing takes 2% of a MacBook in the browser. Believe it or not.
Okay, but I can show you the.
Small.
Yeah. So what it doesn't. So what I have to do because it doesn't fit on my whole screen, I have to put the gate hold. Sorry. Yeah.
And the volume's probably down. 3 oscillators.
Yeah, I'm sorry. I thought it was. I don't know why the gate hold is not. Because sorry, I'm on the hardware interface. Yeah. Yeah. So it's not very loud, but you can hear that there's some sound, and you have this Julius interface, and
yes, the whole Minimoog.
yeah, and it's running on the FPGA, and the interface is running on my host, and that's it.
It's even got feedback. Crazy feature.
So we were quite happy about that. It's such a good demonstration, and thank you, Julius, for having given us this demo.
Hey, I just implemented great design by Robert Moog.
Yeah, of course.
Just Fausted it up.
Okay, that's it. So that's my conclusion slide. So the whole project is on GitHub. So we have already some other people using it. So we have, we have quite make a bunch of work to make it usable by other people. I hope that Nando, you will be able to install it soon. So these are the points that we are studying, and we have this collaboration with CCRMA, which is called Plasma, where so I didn't talk about that, but there are many other applications than low latency to Faust to FPGA, and one of them is using like WFS, for instance, with a large number of speakers, and also using high sample rate for the audio sampling. So I guess that we have been discussing a lot this week, and there are many applications. We've just been talking at Xilinx also, and they are interested by the project. So that's it. And I've so put my slide on Romain's on the CCRMA's website, and I'm ready for questions. You have some more.
Thank you very much.